असतो मा सद्गमय तमसो मा ज्योतिर्गमय मृत्योर्मामृतं गमय.
Very good morning, friends. I am Kamlesh Parihar, Associate Professor, Civil Engineering Department, Jodhpur Institute of Engineering and Technology, Jodhpur, Rajasthan. Today, in this video lecture, we are going to discuss a numerical on Macaulay's method. In the previous video, we have discussed a numerical to find deflections using double integration method. So this Macaulay method, it is not different from the double integration method, rather it is a refined form of double integration method. It simplifies double integration method. Double integration method is easy when the load over the entire span or the equation of bending moment over the entire span does not change. In that case, double integration method is easy. But when there are several point loads or UDL over some part of the span, then the equation of bending moment does not remain same over the whole span. We have to find out mx for different spans. In that case, double integration method becomes very cumbersome. I hope you remember in shear force and bending moment diagram, we need to write equation of mx for every small spans when there were several point loads. Similar was the case with shear force. So there we used to write shear force and bending moment equation for different parts. Okay. So now here we are going to discuss Macaulay method. To appreciate or to understand the Macaulay method, let us take an example. On the screen you are seeing a numerical. In this numerical, there is a simply supported beam AB. With the help of this numerical, we will understand Macaulay's method. Okay. In this beam, there are point load, there is a uniformly distributed load, and there is a point moment. So three different loads are acting, that is point load, UDL, and point moment of 4 kN. These three loads are acting. Now when I will write the equation of mx, then the equation of mx will be different from A to C, then it will be different from C to D, and then the equation will be different for the part D to B. Okay. So Macaulay method will help us to write down a single equation for all these three parts, and then we will find out the deflections. Okay. So in this numerical, what is required? The span is given, the loads are given, and we need to find out the maximum deflection. We need to find out the maximum deflection y max in this beam and the deflection at x equal to 10, that is D point. At these 2 points, I need to find out the deflections. What is given? It is given that the cross section of the beam is given as circular with a diameter of 300 mm. The modulus of velocity of beam is given as E equals 2 into 10 to the 5 Newton per mm square. So all these properties of the beam are given to us, and we need to find out deflection y max in the beam and deflection at x equal to 10, that is point D. X equal to 10 is point D. Okay, so let us solve this question. The first step, the steps in this question are almost same as that of double integration method. Okay, so the first step in the question will be to find out the reactions RA and RB. Okay, so to find out the reactions, we know that the procedure is to find out the reaction. The procedure is take summation of moment about the supports A and B and you will get the reactions. Okay, so reactions I have calculated, and these are found to be 19.43 RA and RB 15.576 Kn. These values are in Kn. Remember, the loads are in kilonewton and the distances are in meter. Okay, so the reactions have been calculated. Then what is the step 2? You all know our master equation. Our master equation, that is EI d2y by dx square equals to minus m. In our previous numerical, we have taken this minus on this side. Okay, this minus was on this side, but here we have applied this minus sign on this side. It doesn't matter. Wherever you want to apply this minus sign, you can. Okay, so by writing this equation, we have EI d2y by dx square equals to minus of m, and the equation of moment m is what? This is our point A, this is our point B, this is point C, this is point D. Okay, so mx is what? Mx will depend upon x. Okay, so let's say first x is between 0 to 5 meter. This is 5 meter, this is again 5 meter, and this is again 5 meter. Okay, now say x between 0 to 5. When x is between 0 to 5, the equation will be RA into x. Okay, this minus sign is outside, so this will be positive. Why? Because RA is sagging. RA is sagging, so it will be positive. So RA into x. Now when x is more than 5, it means x has crossed this. X has crossed this 5 meter. Okay, so 5 less than x, and x will cross, and the equation of bending moment will change. Here the Macaulay method comes into the picture. For this part, C to D, or we can say C to B, the equation of mx will change. So we will make a vertical line. We will make a vertical line here. Okay, and we will write the bending moment equation due to this 10 and 5. So the equation will be minus 10 into x minus 5 and minus 5 into x minus 5 whole square by 2. Okay, so this is called as Macaulay's discontinuity function. Macaulay's discontinuity function. The value of this function will be 0 when x is less than 5. Remember, I again repeat, this portion after the vertical line, this is the Macaulay's discontinuity function. The value of this function will be 0 when x is less than 5. Okay, or you can say apply less than equal to 5. This is the Macaulay's method. Now the Macaulay's method require that this function, Macaulay's method require that this function should be applicable for the entire remaining span. Macaulay फंक्शन की रिक्वायरमेंट है, ये जो फंक्शन हमने लिखा है यह बचे हुए पूरे स्पैन के लिए एप्लीकेबल होना चाहिए. It means this function is applicable not only between 5 to 10, but this function is applicable between 5 to 15 meter. So this function is applicable between 5 to 15 meter. Remember, in this question, this UDL is given only up to x equal to 10 meter, only up to this point. The UDL is only up to D point. But Macaulay's function requires that this UDL should extend up to the point B. ये Macaulay function की requirement है कि ये UDL remaining पूरे span के लिए होना चाहिए. But it is not given. But in this question, it is not the case. So what we do a small adjustment. इसमें small adjustment करते हैं. What we do, we apply a fictitious uniformly distributed load over the remaining span also. And to nullify this UDL, to compensate this UDL, we apply a UDL upward also. Okay, the value of this UDL is same, that is 5 kN per meter. So this is also 5 kN per meter. Okay, and this UDL from bottom is also 5 kilonewton per meter. So what has happened? Now this UDL of 5 kN per meter is continuous over the entire span, and we applied a upward UDL of 5 kN per meter between the portion D and B to nullify this portion. Okay, so essentially our question does not change. Our question is same as the previous question, but we have done this adjustment because it is a requirement of the Macaulay's method that this function should be applicable for the entire remaining span. Okay, this 10 is already applicable, so this was the additional load that we applied. Now since we have applied this additional load, we have to write down the equation of bending moment for the portion DB also. Okay, so there will be one more discontinuity function. Here it comes. This is a point moment of 4 kN per meter. So the bending moment equation between the point D and B is what? Minus 4 times x minus 10 to the power 0. Here 4 is kN meter. It is kN into meter. So there is no need to multiply it with the distance. But here we will multiply it with x minus 10 to the power 0. Here we will multiply it with x minus 10 to the power 0. When we will integrate, this power 0 will become 1 in dy by dx equation, and it will become 2 in equation of deflection. Okay, so this is important. You must remember that these small adjustments which we are doing. So whenever there will be a point movement, we will multiply it with x minus the distance to the power 0. Okay, this is also Macaulay's discontinuity function. These are called as Macaulay's discontinuity function. Now you must remember that this function is applicable only after the point D. This function is applicable only after the point D. So this is applicable for x greater than 10 meter. Okay, so when x is greater than 10 meter, this function is applicable for the remaining entire span, and the value of this function will be 0. This function will be equal to 0. I can say it as a f1 as function 1 and it as function 2. So f2x will be 0 for x less than 10 meter. Okay. So for x less than 10 meter, that is before point D, this Macaulay function f2 will simply be 0. Okay, and after 10 meter this function will be applicable. So this is all about Macaulay's method. This is the way we apply Macaulay's method. Okay, so now let us advance in this question. What is the next step? Simply integration. Okay, so this is our equation, ei d2 by dx square equal to minus of mx, and mx equation we have just written. You can write down this minus sign has been taken inside and the signs has been changed. Okay, and when we will integrate, we will get c1, that is the constant of integration. Okay, integrating it once more, what we get? We will get ei y equal to this equation. Here on integration we will get c1x. Okay, on integration we will get c1x plus c2. So there are two constants of integration, c1 and c2. Now in this question we do not know where dy by dx is equal to 0, because the loading is not symmetrical, so we don't know where dy by dx is 0. So we cannot use this equation ei dy by dx for calculation of c1. So both c1 and c2 will be calculated using this equation. Now the boundary conditions. What are the boundary conditions? We know that in this question at x equal to 0, y equal to 0. Okay, this is mentioned here. X equal to 0, y equal to 0, and hence c2 will come out to be 0. You can put in equation 2. Equation 2. X equal to 0, y equal to 0, so c2 equal to 0. And what is, and x equal to 15, we get y equal to 0, that is at support at B. At B. X equal to 15 meter, y equal to 0. When you will put in this equation, you will get that C1 comes out to be 484. We have to calculate maximum deflection y max. Okay, to find out the maximum deflection, what we do, we make dy by dx equal to 0, because when y will be maximum, then dy by dx will be 0. This you have all read in your 11th and 12th mathematics. Okay, so let us make dy by dx equal to 0. Now one more thing, when we will make dy by dx equal to 0, we must know something. Here we have to make some trials, because the equations of deflection and dy by dx are different for different values of x. Okay, in general the maximum deflection occurs somewhere near the midspan. The maximum deflection occurs somewhere near the middle span. Okay, so we will assume, or in the first trial we say that the y max will occur somewhere between C and D. When maximum deflection is between C and D, then the mx, then the equation of dy by dx will be taken only up to the portion D. Okay, so here it is shown. Maximum dy by dx is between C and D, so this portion is applicable up to C, sorry, for 0 less than x less than 5. This portion is applicable. Then this is applicable for 5 less than x less than 15, and this portion is applicable when 10 less than x less than 15. So this part of the Macaulay's function is applicable for x greater than 10. Okay, but we assume that maximum deflection occurs somewhere between C and D. So x will be less than 10. X will be less than 10. So for x less than 10, this function will become 0 for x less than 10. So this is our first trial where we are saying that the maximum deflection will occur between C and D. So the x will be between 5 and 10, and for x between 5 and 10, this portion will become 0. One more point to be noted in Macaulay's method, that C1 and C2 both will be written in the first part, not in the Macaulay's discontinued function. Both C1 and C2 will come in the first part. Okay, so here we'll make dy by dx equal to 0, and this part will become directly 0. Okay, so when you will put and you will find out that x comes out to be, in the next page with the solution. So dy by dx equals to 0, and from here I have solved it, and I have found that x is 7.3272 meter. Okay, this is the value of x I have calculated after making dy by dx equal to 0, and to find out the y, the maximum value of y, we will put here in this equation ei. Again remember that equation only up to this part is taken, the last part is not used. So here one thing you will note, that we assume that the maximum deflection was between 5 and 10, and x is 7.3272 meter. So this is between 5 and 10. So 5 less than x less than 10. So whatever we assumed was correct. Hence this value is valid and acceptable. Had it been, for example, x had come out to be 11 meter. If x has come out to be 11 meter, then we have discarded this equation. Then rather we have tried for the another equation between x, for x between 10 to 15 meter. In that the whole equation was applicable, and we have to again find out the value of dy by dx, and we have to check that x must fall between 10 and 15 meter. Okay. So x, by putting x equal to 7.3272 meter in y, in above equation, we get y maximum equals to 2299.58 upon ei. The value of ei you can calculate. E was already given as E was given as 2.2 into 10 to the 5 Newton per mm square, and I we can calculate as pi d to the power 4.64. These dimensions are in mm, and these dimensions are in kilonewton into meter cube. So we will convert these into Newton mm. Okay. So these has to be converted into Newton mm. Okay. And on putting the values, we found out that y has come out to be 28.93 mm. I again repeat, please check the calculations. I have done it once. If you find any error in my mathematical calculations, please inform me, I will correct it. Similarly, to find out y at 10 meter, what we do, we simply put x equal to 10 meter, and I find out that y is 24.41 mm, and this is less than 28 mm. Okay, at x equal to 7.3. Okay, so hence this question is over. I have given you the notes. You can study from the notes also, and summarize you in this Macaulay method what we are going to do. In this Macaulay method, whenever there is a change in the equation of moment mx, we will make a vertical line, and then we will write the equation for the other loads. When we are writing the equation for other loads, we must ensure that the equation should be valid for the remaining entire span. Okay, So if it is not applicable, then we will make some modifications in the question, just like as we have done in this numerical, by applying UDL on the above and below the beam, okay, so that the equation for the above UDL remains applicable for the remaining span. Okay, so here in this question we also discussed how to take point load, how to take UDL, and how to take point movement into consideration. So if in any question you find these three types of load, you will use the method as we have used in this numerical. Okay, thank you very much. Please like and share this video, and do comment if you have any doubts. I will be there to solve you. Okay, thank you.